In the last couple videos we studied some of the properties about divisibility. It's now the time to use those properties to prove some other ones about congruence. For all these properties I'm gonna assume I have A, B, A1, A2, B1, B2, A sub n, B sub n, I'm gonna call them all integers, and D an integer, but D will be not zero. So now we can start with the very first property, and this is that if I know that A is congruent with B mod D, then A plus K will be congruent to B plus K mod D for any K an integer. How do we prove this? Well, let's start with this side. This is our hypothesis. So we know that A and B are congruent modulo D. So D divides A minus B. And we can write A minus B as A minus B plus K minus K, because this is 0. And then what we can do is we can reaccommodate all this, so we can have A plus K minus B plus K. This one, this K is this one, and this other K is this one. And then we have some number, this, and some minus some other number. And then using the definition of congruence, we can say that this first number, A plus K, is congruent to the second number, B plus K, modulo D, which is exactly what we wanted to prove. The second property says that if we have A1 that's congruent to B1 modulo D, and A2 is congruent to B2 modulo D, this D is the same in both cases, then A1 plus A2 is congruent to B1 plus B2 modulo D. Let's see the proof. We know these two things. So this tells us that D divides A1 minus B1, and also D divides A2 minus B2. And we saw in a previous video that if we had that D divides X and D divides Y, then D divides X plus Y. So here we will have that D divides A minus B1, A1 minus B1 plus A2 minus B2. And we can rearrange this to have A1 plus A2 minus B1 plus B2. And with this we can use the definition of congruence. So we have some number minus another number, then the first number, A1 plus A2, is congruent to the other number, B1 plus B2, modulo D, which is exactly what we wanted to get. The third property is also very simple. If we have that A is congruent to B modulo D, then for any C, an integer, we know that C times A will be congruent to C times B modulo D. Let's see the proof. So we know that A is congruent to B modulo D, so D divides A minus B. And we saw in a previous video that if we had this, then D would also divide C times A minus B. And we can use the distributive here and say that D will divide C times A minus C times B. And then we use again the definition of congruence, and we have exactly what we wanted, that C times A is congruent to C times B modulo D. Now the last property can be a bit more tricky. What it says is that if A1 is congruent to B1 modulo D and A2 is congruent to B2 modulo D, then A1 times A2 is congruent to B1 times B2 modulo D. Let's see the proof. A1 is congruent to B1 modulo D. Then D divides A1 minus B1. In the same way, D divides A2 minus B2. And now let's use the definition of divisibility. D divides A1 minus B1, then there exists an integer k1 such that A1 minus B1 equals k1 times D. Another way of writing this is that A1 equals k1 D plus B. And the same here, we have that there exists an integer k2 such that A2 minus B2 equals k2D. So A2 equals k2D plus B2. Let's now write the product A1 times A2. A1 is k1D plus B1. A2 is k2D plus B2. Now let's use the distributive. We have this one would be distributed like this, and then this one would be distributed like this. So what we have is k1D times k2D plus k1D times B2 plus B1 times k2D plus B1 B2. And what we can see here is that these terms all have the letter D. So let's take d as a common factor. For those three terms, we have that d will be multiplying k1, k2, d from this one, plus k1, b2, plus b1, k2. And then we have the other term, b1, b2. We can now move this term to the other side, and we would have that a1, a2 minus b1, b2 equals d times all this number. Now if we look at this number, it's an integer. So what we can do is we can call this number we can just call it a general number k. That would be an integer. So what we did was write a1, a2 minus b1, b2 as d times some number k. But this is using the definition of divisibility. This tells us that d divides a1, a2 minus b1, b2. And then we can use the definition of congruence, which will tell us that a1, a2 is congruent to b1, b2 modulo d, which is exactly what we were trying to prove. Now, in a similar way to the property number 2, we have another one, that if a1 is congruent to b1 modulo d, a2 is congruent to b2 modulo d, and so on. We have a list of a sub n's and a list of b sub n's that they all satisfy that a sub n is congruent to b sub n modulo d. Then we can prove two properties. The first one is that the sum of the a sub n's is congruent to the sum of the b sub n's modulo d, and that the product of the a sub n's is congruent to the product of the b sub n's modulo d. This is very similar, the first one, to property number 2, and you can prove it with induction. And the same for this one. This is similar to property number 4 with induction. I will not be proving them because they're very trivial, and the basis step is what we did in property number 2 and number 4. And then induction, if you don't remember induction, you can go back and check the other videos. Now I will do the last property, which is that if A is congruent to B modulo D, then A to the power n is congruent to B to the power n modulo D. And the proof for this is actually very, very simple, because once you've proven this property, that the product of a1, a2, and an is congruent to the product of the piece of n's modulo d, then all you have to do is take a1 equal to a2 to a3 and so on equal to an, and also take b1 equal b2 equal b sub n. And what we'll do is call all the a's sub n equal to a, and all the v sub n's equal to b. A and b are the numbers given in our hypothesis. So then, using the property 6, we know that a times a and so on times a n times will be congruent to b times b times b n times modulo d. And this is exactly what we wanted to prove, that a to the power n is congruent to b to the power n modulo d.